Welcome to Atomic Structure Part 2, all about the electrons and the atoms and how we believe they're structured. All right, so in order to talk about electrons, we have to talk about electromagnetic radiation because the big source of evidence for what the model of the electron structure is via light data. So let's talk a little bit about some vocabulary. Definition of a wave. It's a transfer of energy via oscillation. That could be oscillation of matter if you're talking about sound waves, or it could be oscillation of electric and magnetic fields if you're talking about light. Wavelength is a key characteristic that you need when you're talking about waves. It's the distance from one trough to another, so the distance between the oscillations. Or it could be trough to trough, either way. Frequency is another important variable, and it is the number of peaks that pass a given point each second. So it depends on the speed. Its unit is hertz, which you will see symbolized as an Hz, or you can see it as seconds to the -1 because it's cycles per second, and you don't really use the cycles part of the unit. So the velocity of a wave is defined as the distance a wave moves in a unit of time, and its velocity is frequency times wavelength. So if you take frequency, which is cycles every 1 second, and you multiply it by the distance of a cycle, then you get the distance, the meters per second. For light, the speed of light, the V is substituted with the C as 3.00 times 10 to the 8th meters per second. Really fast. All right, back up for some history again. Newton originally thought light consisted of particles. Here's a quote from his paper about the topic. I'm not going to read the whole thing to you, but he thought they were diffracted by prisms or water droplets based on their size. So bigger particles were refracted least, and they were the weakest, the most, and then the ones that were refracted the least were the stronger colors, like the red. Maxwell thought light was a wave phenomenon. Here's a little video to give some evidence for the wave nature of light. Okay, do you see that right now there? The light and the dark patterns? That's what we're looking for. Okay, so keep watching. There. Now you can see them nice and clearly. What's happening is that if you consider light a wave, the wave goes through those slits and they get diffracted. They bend through the slits. And then when they encounter another wave, sometimes they hit peak to peak, and so they get to be a bright light. Sometimes they hit peak to trough and they cancel each other out. And so that would only be seen if light was considered a wave. Okay, that's all we need of that. So let's go back to the keynote. He even was able to calculate the velocity of an electromagnetic wave and found that it was the same for light. So infrared radiation, UV radiation was the same as visible light. And he was able to characterize it as the electric field versus the magnetic field, and found that it did have a wavelength and a frequency, just as Newton thought the particles had, but now he's thinking they're more of a wave. Okay, Einstein brought back the idea of the particle idea because he discovered something called the photoelectric effect. Let's watch a little bit about that.
This tutorial will cover the photoelectric effect. Light exhibits wave-like properties, such as diffraction and interference. As a result, at the end of the 19th century, it was generally accepted that light was a wave. However, when studying the photoelectric effect, light appears to exhibit particle-like properties as well as wave-like properties. The photoelectric effect is the effect whereby when light is shone on a metal surface, electrons are given enough energy to escape from the surface. The way in which the electrons escape can be studied with this equipment. Two metal plates are arranged, with one of the plates exposed to the light source. The electrons liberated from the metal travel across to the other plate, causing a current to flow. This is known as the photocurrent. The photocurrent is detected as soon as the light turns on, suggesting that light is acting as a particle. If light were a wave, the energy would build up slowly on the screen. The particles start knocking electrons off the surface as soon as the light is switched on.
This is just like what's happening with your solar-powered calculator or anything else you have solar power. It doesn't require time, it happens automatically.
It was found that the photocurrent flowed when ultraviolet light was shone on the metal, but not when the red light was shone on the metal. This was observed no matter how intense the beam of red light was. This suggests that the light is made up of particles which have an energy that depends on the frequency of the light. This can be demonstrated by analogy. If you fire a high-energy photon at an electron, you will liberate it from the metal. Correspondingly, if you fire a cannonball at an elephant, you will knock it over. In the same way, no matter how many low-energy photons you fire at an electron, you will not release it from the metal. Correspondingly, you can hit ping-pong balls at an elephant as long as you want, and you will never knock it over. The energy needs to be delivered to the elephant in one go.
All right. I like that analogy. All right. So today, we don't have a perfect theory. We talk about light being a wave and a particle at the same time, exhibiting whatever property you're looking for. Now, Max Planck found a way to describe it mathematically a bit better. He was studying black body radiation, in which if you heat a black body up, it radiates different colors that are dependent on the temperature of that body, because the particles are moving and gaining more and more energy, and they're releasing the light related to that energy. So he decided that light was made up of bundles of energy called photons. The energy of each photon is proportional to the frequency of the light. And so the higher the energy, the different the color is when it's released, and that's a higher frequency of the light. Blue is a higher frequency than yellow, than orange, than red. He came up with a proportionality constant, E equals HF, where E is the energy, F is the frequency, cycles per second or hertz, and H is Planck's constant. It's just basically a slope of the line of a graph between energy and frequency, which is 6.6262 times 10 to the negative 34th joules per second. We'll come back and use that equation in a little bit. All right, so now let's put our attention back to atoms and electrons. A bright line spectra occurs when electrons in an element are excited by heat or electricity. When the electrons release that energy, light is emitted. Each element has its own unique set of lines characteristic for that element. I think there's a diagram. To electrons. There is a bright line spectra produced. That's what this is down here. It occurs when electrons in an element are excited by heat or electricity. When the electrons release that energy, light is emitted. Every element has an individual fingerprint that would be its spectra. You can see one here vertically, and here this one's horizontally. It was produced when light went through a slit in a prism or a prism, and the light was diffracted to different amounts, and therefore it's showing all the different energies of light that are coming from that element that's been excited. The energy in a photon of light is directly proportional to the frequency of light. So the higher the frequency, which means it's more toward the blue end, the higher the energy. You can find the energy of a single quantum of radiation at any given frequency using Planck's equation that we saw, and that proportionality constant is Planck's constant. Well, it's really small, but let's go for it anyway. Example, a spectral line has frequency of 3.5 times 10 to the 12th hertz. What is the energy of the photon? Okay, so here's the equation. E equals HF. H is 6.6262 times 10 to the negative 34th joules seconds. So you calculate this by putting in the frequency, 3.5 times 10 to the 12th cycles per second, times Planck's constant, and you can see that the seconds cancel out, leaving you with cycles joules, which is the joules of a wave, which you should get 2.3 times 10 to the negative 21st joules. Okay, so here's Bohr's model. He said that there's different orbits in which an electron can travel. Okay, we knew the electrons were on the outside. Each orbit is at a fixed distance from the nucleus. The greater the radius of that orbit, the greater the energy of the electron. So this n equals 3 electron has greater energy than n equals 2 and n equals 1. And for some reason, he believed they were confined to those set orbits. These are known as energy levels. And when an electron gets excited, it can move from one energy level to the other and then fall back down and release the light that it absorbed. Okay, so when all of the lowest energy levels are occupied, the atom is said to be in its ground state. When the electrons are filling in from closest to the nucleus on out, that's the ground state. When you hit it with light or electricity, that excites some of the electrons up to a higher energy level, and they have to absorb just that certain amount of energy that would get them to the higher level. And they're unstable up there, so then they fall back down and they emit the light. So the bright line spectrum of an element represents the absorption of energy and the re-emission of energy. And they're specific to a specific element because there's a certain number of electrons in certain locations for an individual atom. And therefore they'll have a different set of lines for each kind of atom. Love that. Problems with Bohr's model is that it only explains some of the lines in the bright line spectrum. He could really only mathematically describe hydrogen. So the math didn't generalize well enough to everything. And it still didn't explain why the electron didn't fall into the nucleus. What it did do was quantize the electron. So he said they could only be in those certain places. And that explained some of the emission lines that he saw. So it was a start. And next time we'll talk about the modifications made to make it work.